Thank you everyone for coming today. Hello, my name is Genzi.
I'm Dinesh.
I'm Jerry.
I'm Alex.
And I'm Tony.
And we're team 14928 from Richard Montgomery High School in Rockville, Maryland. So this year's challenge was themed around the cost and the widespread use of the internet. And with COVID-19 moving many workplaces to a virtual environment, this is an especially pertinent issue. And understanding how the internet's being used and how it's changing will allow us to better understand how we can adapt our behavior around it.
For problem one, we had to build a model to predict the trend of bandwidth price over the next decade in the US and UK. For problem two, we had to build a model for figuring out bandwidth use in a given household. For problem three, we had to build a model to determine the optimal number of cell towers in a given region.
Let's start with problem one, where we used an exponential function to model internet prices over the next decade. Going in, we wanted to address A, the rapid expansion of 5G internet, and which would dramatically increase bandwidth efficiency, and B, the observation that internet use is higher in urban areas versus rural areas, as our model should be applicable to both.
So our model had three major assumptions. So first, we assumed that the current rate of internet growth would be constant for the next decade, which allowed us to assess the trajectory of current growth and didn't necessitate speculation on the potential economic scenarios in the future. Second, we assumed that the price of internet plans would stay constant. And similar to the first assumption, this gives a baseline projection of the current trends. And third, we assumed that bandwidth use in rural areas was half that of urban areas, which gave us a good estimate based on other countries that we could use in the absence of data for the US and UK. So with these assumptions in mind, we began to develop our model. So we need to calculate the rate at which internet price increase. So we need to figure out the amount of money needed per each unit of bandwidth. And in line with Moore's law, which says that technological capabilities increase exponentially, and observed trends in past data, we predicted that data usage would grow following a simple exponential equation.
Now we'll incorporate this idea to model US internet prices. For the US model, we broke down the ratio from the previous slide into the cost in the numerator and our exponential model for bandwidth use in the denominator. Our model for UK internet prices was very similar to the US, but with two added components to account for rapid 5G adoption. We introduced the function A of t, which describes how much of the population has adopted the internet, and big G, how much more efficient the next generation internet is. The function A of t was calculated with data from Outen et al., who calculated 5G adoption in the UK over the next decade, using a polynomial regression to model the trend line of their data points. Finally, using the info given to us by M3, we calculated the ratio of 5G efficiency to 4G efficiency to find big G, which was approximately 6.67. In order to determine the values of the remaining parameters, we used data from each region and ran an exponential regression. However, the data provided about bandwidth usage was limited and only available for the past 5 years. To mitigate potential random error from this, we ran Monte Carlo simulations to generate more random samples from the existing information. For instance, for the rural UK, we created 10,000 simulations of bandwidth usage based on Ofcom data from 2015 to 2020. Exponential regressions were then run on each of these data sets, and the averages were used in our final model. After substituting the values of each parameter into our model, we obtained these results. Our results predict that a megabit per second of data would cost less than a cent in both rural and urban areas in both the UK and the US. Data would be the most expensive in the rural US and the least expensive in the urban UK.
To obtain these results presented by Dinesh, we assume that the monthly cost of internet was constant. However, due to natural fluctuations, the cost of internet slightly varies over time. Since this variance will result in error propagation, we introduce an uncertainty of plus or minus 10% to account for these fluctuations in all four categories. Our results offer us insightful predictions about internet usage. First, that the cost of bandwidth will drastically decrease in the near future, meaning that our everyday demand for bandwidth will continue to increase. Furthermore, for both the US and UK, rural costs of bandwidth are much more expensive compared to urban costs. As the internet becomes a necessity in our everyday lives, equity to internet access may become a big societal problem in the future.
let's move on to the second problem, bit by bit. In this problem, we generated a probability distribution function that would allow us to see the probability that a household would use a given bandwidth at any point in time. This model was generated using a Monte Carlo simulation and takes into account a variety of different factors, such as age, occupation, and time spent on various internet activities. The reason we chose this approach was because we believed that there were three major factors that would affect bandwidth usage. The first is age and occupation. Different people will use different quantities of internet based on their job and age group. The second factor is the different internet activities that people would participate in. Different activities such as streaming or web surfing use different quantities of bandwidth. And third, and most importantly, we wanted to capture the additive nature of bandwidth. Because different individuals may use different amounts of bandwidth at any given time, this can create spikes in bandwidth usage, which may influence the bandwidth needed to capture 90% and 99% coverage.
Our first major assumption was that the only internet activities are video streaming, web surfing, gaming, and video conferencing. This was mainly to help focus the model and to limit the number of variables used. Our second major assumption was that people only do one activity at a time. And our justification for this is that multitasking is difficult to quantify. To develop our model, we created a simulation to randomly generate the bandwidth that is used by a household at any point in time based on a set probability distribution of activities. Essentially, we have a random variable b, which is the sum of the bandwidths for each person in the household. To determine the probability of doing activity, we designed our hours model.
Simply put, the hours model takes into account an individual's age and occupation in determining how much time someone spends online. To simplify this, we divided time online into two categories: time spent online for work and education, and time online spent for leisure. In other words, time that is spent online not on work or education is time that is spent on leisure. Within these categories, we can subdivide them further into the activities. Under work and education, we have video conferencing and web surfing. And under leisure activities, we have web surfing, video streaming, and gaming. Now, the last step is to use the information that was provided to us by M3. According to the Internet Media Consumption Group, age groups spend similar ratios of time on various leisure activities. However, based on their occupation, they may have different quantities of leisure time. Thus, to determine the amount of time spent on work and education versus the time that is spent on leisure, we conducted research on various jobs and used our own experience as students to calculate the time that is spent on work-related video conferencing and web surfing. From there, leisure time can naturally be deduced by subtracting work time from the total time spent online, which was also taken from the Internet Media Consumption Group.
We can now apply the hours model to the bandwidth interaction model. To do this, we created a Monte Carlo simulation that generated 1 million possible bandwidths at any point in time, generating activities based on the probabilities in the hours model from before. This allows us to capture all possible ways that a household may use the internet, as well as spikes in internet usage. From this, we need to find the minimum bandwidth at which 90% and 99% of the values fall under. In addition, due to factors such as interference and router distance, bandwidth is typically reduced by 35%. Thus, the final step is to multiply our value by 100/65.
We applied the Monte Carlo simulation to each of the three households in the problem. The values shown are quite surprising, but they do make sense. Oftentimes, we see companies advertising 100 megabit per second internet speeds. But from this investigation, it appears that only a fraction is really needed. And this makes sense, as activities such as web browsing do not require much bandwidth. However, for large downloads, which were not included in this analysis, higher bandwidth speeds are often convenient.
In our model, we assume that everyone is using HD video streaming, while in reality, there are other types of video streaming, such as 4K, which uses significantly more bandwidth. For our sensitivity analysis, we ran the Monte Carlo simulation using 4K video streaming values to see the change in the results. While the first two households' bandwidth increased significantly, the third household had a relatively low increase. In our model, household 3 was composed of college students who spent most of their time studying or working, leaving little time for leisure. These differences reflect the flexibility of our model in encapsulating different scenarios. Overall, the large increase in bandwidth requirements shows that as technologies advance, we need to use significantly more bandwidth than before.
So for our third model, we use a geometric approach to calculate the optimal numbers of cell towers for each subregion. And using information such as population size and age distribution, we incorporated components of the bandwidth interaction model from problem 2 into this model.
We used this approach because we wanted to account for a region's varying demographics, such as age and occupation, while including random spikes in bandwidth usage. Incorporating the bandwidth interaction model from problem 2 created a more flexible estimate.
And in addition to all the assumptions that were made in problem 2, we also assumed for this model that people were evenly distributed in each subregion, since we were only provided info of the overall density of a region, and having a standard density would prevent the number of towers needed from being arbitrarily skewed in the absence of data. And we also assumed that the overlap of tower ranges was pretty negligible, because consumers would typically appreciate multiple towers being nearby because it would give them better connection.
We'd like to start by giving a visual example of our approach. Say we have a region with area 200 miles squared. To cover all households, it has a bandwidth requirement of 8,000 megabits per second. Now say we have a cell tower that is arbitrarily set to cover 100 miles squared and can provide 5,000 megabits per second backhaul capacity. In other words, the quantity of bandwidth it can provide to all individuals. It's easy to see that we just need 200 divided by 100 miles squared equals 2 cell towers to provide full area coverage. These 2 cell towers are also enough to cover the bandwidth necessary for the region. However, this is not always the case. Take the second example where bandwidth needed by the same region is 20,000 megabits per second. In this case, after following the same process as before, we cover the whole region geographically, but not bandwidth-wise. Thus, we need a multiplier to multiply the number of cell towers we have. We can determine this by simply taking the bandwidth needed and dividing it by the bandwidth provided by the cell towers. Thus, our multiplier in this example is 2. So we need 2 times 2 equals 4 cell towers.
Mathematically, Jerry's explanation is represented by the following equation. The first fraction, or the area of the subregion divided by the area that each cell tower covers, describes the geographic minimum of towers required to cover the entire subregion. The second fraction, or the amount of bandwidth needed per area, divided by the amount of bandwidth provided per area by the cell towers, describes the multiplier to cover bandwidth needs. The ceiling function ensures that the model returns the required number of towers. To capture the 2 possible cases Jerry brought up in the visual example, we can create the following piecewise function. If the bandwidth density needed for the subregion is greater than the bandwidth density the minimum number of towers can provide, then we must incorporate the multiplier as shown in the middle formula. However, if this is not true, the minimum number of towers to cover the geographic region is sufficient, which is described in the leftmost formula. The final model is obtained by combining these 2 functions.
Finally, we can determine the bandwidth needed for each subregion by using the bandwidth interaction model from problem 2. Though we are given the age range, we are not given occupation data. As a result, we use an additional Monte Carlo simulation to randomly generate households with different occupation-related hours for each individual. Simulation allows us to capture millions of different possible households and job combinations, and also capture the spikes in data usage.
Once this is done, we obtain the following bandwidth needs for each subregion. Applying these bandwidth values into the final towers model yields the following results. 15 towers are needed in region A, 42 in region B, and 12 in region C. These values make sense, given that region B is much larger than the other regions. These values show that both bandwidth usage and land area heavily influence the number of towers needed. Our model used 2 Monte Carlo simulations, one for determining households and occupations, and another within the bandwidth interaction model to capture bandwidth usage fluctuation. Incorporating these 2 simulations helped us create a more flexible model, which can capture a broader range of different regions. Additionally, our model is highly sensitive to backhaul capacity and cell tower radius. For example, increasing backhaul capacity would drastically decrease the towers needed.
Ultimately, the internet is becoming a larger part of everybody's lives, especially now with COVID-19. The models we created in each of these three problems reveal many important facets of how the internet is currently evolving. The first model revealed that internet costs will significantly decrease over the next few decades. The second problem showed that internet bandwidth usage is often not as high as companies portray. And the third problem revealed how cell tower placement is largely dependent on bandwidth usage and tower coverage. Thank you so much for listening, and we really appreciate your time, and we'd love to take any questions.
Thank you all so much for the presentation. So we will take questions in a minute, but before we do, let's give the students a round of applause for the great presentation and great work. Okay, so we'll start with questions. I'll start with a question about your part 2 Monte Carlo simulation. Would you actually mind scrolling back to slide, I think it was slide 20?
Sorry, just give me a moment so I can.
Yep. Yeah, no rush. Or maybe it was one before that, actually, slide 19. Okay, awesome. So I had 2 questions about this Monte Carlo simulation. I think you said you ran it for like a million trials, which a million is definitely a large number. And I wanted to understand, how did you choose that number? And how did you know it was sufficient, or could you possibly have gotten away with less trials? How, in general, for these Monte Carlo simulations, how do you go about choosing how many times you run it?
Sure, I can help. Okay.
Okay, Jerry,
go ahead, Tony. Okay, sure. So in this case, the Monte Carlo simulation, we chose the number of trials to run based on our experience and based on simply the logical way that this bandwidth interaction model functions. Because there's only a limited maximum number of bandwidth that can be used based on our assumptions that there are only, I believe, 4 types of internet usage. There is a maximum that is involved in terms of bandwidth usage. And if there wasn't a maximum, we think that running an even greater number of Monte Carlo simulations would be beneficial. However, because there is a maximum number of bandwidth that can be used by this family, given our assumptions, we believe that limiting it to 1 million would be sufficient in capturing the whole range from 0 megabits per second used to that maximum. And it incorporates everything that is shown in between. And Tony, if you would like to add on to that.
Yeah, definitely. I feel like since we only had so many possible activities, 1 million is sufficient to calculate it. We ran more than we actually needed. 100,000 probably would have been enough too. 1 million was just to ensure that it was as accurate as possible.
And would there be a way to check if 100,000 was enough, or is that a sense of like a feeling, or you have some concrete evidence for that?
Yes. So
personally, I ran 100,000 a few times, and the values are basically the exact same as 1 million.
Okay, perfect. Makes sense. Great. Thanks, guys. I have one other quick question about this plot here. So it has your probability for bandwidth has like this, it almost looks piecewise linear. It drops down close to 0 at some points. I was expecting maybe something that looked more random. So I wanted to understand, why do you think that this probability distribution has such strong structure, and why are there certain bandwidth needs that have very low probability on that plot?
Yeah, I can take this question.
Okay, sure.
Okay. Because in our thing, we defined only like specific bandwidth usages, like streaming, we used HD, which is 5 megabits per second, and like web surfing, which is another specific value. Some values are like very hard to reach because it would require like a specific sum of values, whereas other ones could be reached in multiple ways. And so that's probably one of the limitations of our model, because we assumed like each activity only had like one specific bandwidth. It resulted in this structure.
Okay, great. Thank you.
I've got a couple of questions. This is about the technical computing challenge. How much of your you included some code in the appendix to your paper. How much of your presentation today is covered by that code? And are there things in the presentation today that the code didn't do, you've done since then?
Yeah, so I think the biggest change that we've made since then, just to revise a few minor errors, was mainly in our solution to mobilizing mobile. And this is simply because in our solution to mobilizing mobile, the initial formula that we used didn't too accurately capture the dimensional analysis component of the solution we wanted, where we wanted the number of towers per region. In our initial formula, we swapped a few of the constants by mistake. And so in the end, I personally would estimate that the code that we created really helps to capture maybe even 70% of what we designed in this, because bandwidth usage just makes such a fundamental part of both problem 2 and problem 3, because our solutions are based off of that. And in problem 1, it really helped us address a lot of the problems we had regarding the lack of data, and by simulating some additional data sets using multiple pieces of information from multiple pieces of research, it allowed us to create a more flexible and accurate estimate.
Okay, we got to go on. Last night at the Academy Awards, one of the telephone companies advertised that they are now offering, in some areas, gigabyte internet. Now, you don't have any bandwidth over 100 megabytes in anything you talked about. So your model, your analysis differs by an order of magnitude from what Xfinity is thinks they can sell. Who's right? Is your models right, or are they right?
I think both parties here are right, because of course the number one priority for these cell companies is to advertise how great their internet speeds are: 1 gigabyte per second, 2 gigabytes per second, maybe even more. I mean, all of those numbers seem really, really attractive to consumers. But ultimately, I think what our model shows is that while these numbers look super attractive, in day-to-day life, we often don't need that much internet speed. While, as we mentioned, while this really fast internet speed may help with downloading super large files quickly, taking a minute rather than 10 minutes.
I'm not asking whether high-speed internet is a good idea or not.
Mm-hmm.
Sure, we could. Yeah, I'm asking, is your model right, or is their estimate of the market right?
Well, I think in this case, our model.
Why doesn't your model predict any gigabyte usage?
Yeah, so in our model, we didn't include for those large downloads, and those large downloads do take up a lot of bandwidth. However, because we focused on the 4 activities: web streaming or video streaming, web surfing, video conferencing, and gaming in general, those typically required very low bandwidths as provided by the M3 data. They took around 5 megabits per second for things like video streaming at HD, I think 3 megabits per second at web surfing. So all of those contributed to the lower numbers. And of course, as technology grows, those bandwidth requirements may also grow, reflecting some of the larger internet speeds.
So you're saying your model doesn't include any of activities that require high bandwidth. That's why it doesn't require high bandwidth. So
yes.
I think the difference is that all of these activities aren't really common in day-to-day life. Like, you're not going to go around like downloading like 2 gigabit files like every single day. So I think our model more captures.
I'm not justifying the model, but
okay.
I'd like to add that our model asked for how much bandwidth you need, the minimum bandwidth you needed for 90% or 99% coverage. Just because like you're doing very large file downloads like 1% of the time, that doesn't mean that's like the bandwidth that you need. So that justifies our model.
Great. So I'm asking critical questions, but I like what you've done. Good job, guys.
Great, thanks. Do we have any questions from other judges? We have about 3 minutes left here.
So in your first question, your response to the first question, to get the regression for your geometric series, you have a distribution, normal distribution that you assume you know or I should say you calculated a mean and standard deviation, and then you calculate numbers based on that distribution, what extra information does the regression on those numbers give you?
So I can answer this. So we're referring to the first question, right? So
Yes.
basically, because we had a very limited amount of raw data, when we ran our 10,000 Monte Carlo trials, we basically just simulated a lot more data values so that we can get a more accurate, per se, gauge of what our parameters were. So like the constant values. And when we ran the regression, we wanted to just get a larger data set essentially because of the lack of raw data that we had. So it just gives us more insight by simulating more data sets.
Mm-hmm. To add on to that, I think when the judge was asking that, when you generate the Monte Carlo data sets for one sample, for example, and you take the average of that, of course, it's very likely going to return the same average from the low data set sample that we obtained. So what we also did was we actually incorporated various other research samples as well into that Monte Carlo. So we generated essentially a set of distributions, and then we looked a little bit at the overlap of those distributions to look at where there was a lot of commonality. And by doing that, we hopefully got a slightly more accurate model, which also includes things like the standard deviation as well. So if the standard deviation was larger and we looked at the overlap between where those varying different research papers came from, then that would give us a slightly better estimate and a better general picture at what the data looked like.
Okay, thank you.
Okay, great. So we are unfortunately out of time, but thank you so much for the presentation, for answering our questions. I just wanted to remind you that of the hundreds of teams that participated in the math modeling challenge this year, you were a top 3 technical computing team, which is really impressive. We were really impressed with and really proud of all the work you did. And that goes not just for the judges that are here, but all of the other judges who can't be present who read your work at different stages of the review process. So I just wanted to congratulate you again, and we're excited to see you at the awards ceremony this afternoon. Thank you all.
Thank you so
Yeah,
much for
thanks,
also
guys.
judging.
Thank you.
Thank you very much.
Thank you. Bye-bye. And have a great rest of the afternoon.
Goodbye. Have a great rest of your day.